Hello, everyone. Today we will start our lecture series on statistical analysis and inference. This is a three-lecture series in which we will talk about sampling and estimation, hypothesis testing, and analysis of variance. So let's start with the first topic, sampling and estimation. Suppose you want to answer the questions that I have listed here. What percentage of refrigerators produced by a manufacturer may have defects and may fail before the expiration of their warranty? Or what is the average height of men and women in a particular country? Or suppose you have a coin and you want to know if that coin is fair. In all these questions, you have a population of all the refrigerators produced by a manufacturer, population of all men and women who live in a country, and you want to draw some conclusions or make some decisions about this population. In reality, however, you may not have access to the entire population. For example, if you want to know what the average height of men and women is in the US, you could, in theory, go ahead and measure everybody's height in the country, but that's not a feasible thing to do. In certain situations, it may not even be possible. Imagine you have a coin, you want to know if it's fair. What is the population of all the possible tosses of a coin? That basically is a list that goes to infinity. You can sit here until the end of time and keep tossing that coin, and you still have not exhausted all those possibilities. So because of this, the population parameter that we're interested in, like the percentage of refrigerators who have defects, the average height of men and women, these values are usually unknown. So one question would be, what can we do? Now, what we can do is instead of testing the entire population, we can take a sample from it and try to find the statistical characteristics of the sample. Then we can make decisions about the population based on the information that we obtain from the sample. For example, what is the average height of the adults in a country? Well, take a sample of 1,000 people who live in that country and measure their heights and find the average. How many refrigerators will fail before the expiration of their 3-year warranty? Take a sample of 100 refrigerators and test their lifetime. Is a coin fair? Toss it 200 times. Look at the number of times you get head or tail. Now, the question that we want to answer in this lecture is this an acceptable approach? Can we make inferences from a sample and then generalize it to the entire population? Now, in this case, what we have is a population of size n, what I'm showing here. And you have a parameter of interest. Notice that we usually go with population parameter, both of which have the letter P. This population parameter of interest, let's call it theta. We take a sample from this. This is a random sampling, so each of those sample values would be an independent random variable from that population, giving me this sample. Then I can analyze that sample and find the sample statistic. And notice that both letters start with S. So we usually go with the notation of population parameter and sample statistic. Population parameter is theta. Sample statistic, I show it as theta hat to indicate that this is an approximate value and not an exact value. Then once you have theta hat, you can make statistical inference about what the value of theta might be. Now, one thing to know is that that estimator, that theta hat, is a function of random variables because each of those samples that you take is a random variable. So theta hat itself is a random variable and has a PDF. It's not that you will get one fixed number. So theta hat, your estimator, will have a sampling distribution. We show this as f of theta hat. Let's look at this example. Imagine you have a population of 3 balls, one of which is 1 pound, the other two are 2 pounds and 3 pounds. And you don't exactly know how many balls you have and what weights they get. So you're interested in knowing what the mean weight of the balls in that population are. So what you do is you take samples. Now, this, of course, is a very simple example, but I'm using this only for demonstration purposes. So imagine in the first sample, you pick two balls randomly. One is 1 pound, the other 3 pounds. So your mean is going to be 2 pounds. For the other sample, let's say randomly you choose the 1 pound ball and the 2 pound ball, mean being 1.5. And for the third sample, let's say 2 and 2, which will give you a mean of 2. As you can see, each sample, because it is a random value, would give you a different value for the mean. So now what I can do is I can look at all the possibilities. If I pick um, the 1 pound ball first and then put it back in that bag, and just so happens that I pick it up again, the mean weight is going to be 1. So this is sampling with replacement, if you will. If I pick the 1 pound and 2 pound, the sample is going to be 1.2. 1 and 3 is going to be 2, and so on. And then if you look at the histogram of the values that you can get, you will see that this being the distribution function for your um, estimator, which in this case is the mean of the sample, would have a distribution itself, which is normal in this case. Um, Most likely you're going to get 2 as the mean value, which is the correct value for the population. But it is possible that based on the sample that you get, you incorrectly assume that the mean weight for the population is 2.5 or 3 or 1.5 or 1. It is more likely that you uh, get that number 2, but again, that's a random variable, so there are no guarantees. So that would be the distribution of the sample mean. Now, what is an ideal estimator? Obviously, an estimator will have a PDF. So your theta hat is going to have a distribution function. Ideally, we would like this estimator to be unbiased. Now, in statistical analysis, bias means systematic overestimation or underestimation. If theta hat is an unbiased estimator, that means on average, its expected value would be the same as the value of the population. The expected value of the mean weight of the sample of the balls that I took would ideally be the mean weight of the entire population. So we define the term bias for an estimator, which is the difference between the expected value of the estimator and the actual parameter of the population. And again, ideally, we would like this estimator to be unbiased, meaning that if this is your expected value of the estimator based on the distribution that it has to fall exactly on the population parameter, so that EF theta hat should be somewhere here. So the situation on the left, that's an unbiased estimator. The situation on the right, it's a biased estimator, because as you can see, the mean of the sample estimator is actually not the same as the population parameter. Not only we would want the estimator to be unbiased, we don't want it to give us too much variation. Consider the example I gave you in the previous slide. You could get 2, you could get 2.5, 3, 1.5, or 1 as the mean of the sample. This is not good, because if you get 3 or 1 instead of 2, these are very different from the actual mean weight of the population. So ideally, what you would like to see is a situation like this, in a sense that not only the mean of the sample distribution is the same as the population parameter, it does not give you a lot of variability. So the values you will get would be pretty much close to theta anyway, compared with the one on the left, despite the fact that it is unbiased, meaning that the sample distribution has a mean equal to the population parameter. You may in fact get a wide range of values that could be very, very different from the population parameter. So two things that we want is our estimator to be unbiased and have a low variance. Now, let's take a look at a few examples. And a lot of these examples might actually come very, standard to you. You're not going to be surprised, but we have to be able to mathematically prove that these estimators are unbiased. So consider the first one. What is an estimator for the mean or the average of a population? One natural thing that might come to mind is we can take a sample and then find the mean or average of that sample and assume that that value is the same as the mean or average of the population. Let's see if that's the case. So suppose I take a sample of size n, and I have n random variables yi. These are observations that are independent of one another, taken all from the population. I sum them all and then divide it by n. This is my sample mean. Let's see what the expected value of the sample mean is. Expected value of y bar is the expected value of 1 over n times that summation. I can take 1 over n out of the summation, and I can have summation of the expected values. Each yi is a random variable taken from the population. And assuming the population mean is a value, let's say mu, each one, the expected value of each of those observations would be the mean of the population. So you basically have mu n times added together divided by n, which is mu. What does that tell me? That tells me that the expected value of the sample statistic is actually the same as the population parameter. Now, again, this may not come as a surprise to you. This is something that we normally do, even when we don't look at it from a statistical perspective. But from a statistical analysis perspective, we have to make sure that this is an unbiased estimator before we can use it. And the good news for us is it is an unbiased estimator. Let's also see what variability we get for this sample statistic. So variance of y bar, which is the mean of the sample, is the variance of, again, 1 over n times summation of yi's. Take 1 over n out, becomes 1 over n squared, because that's a variance. Variance of yi. Yi, again, each yi is taken from the population, so it has a variance of sigma squared. Added together n times divided by n squared, and you will get sigma squared divided by n. What does that tell me? That tells me that if you take larger sample from that population, the variations within that sample statistic would be less because n goes up, meaning that the variability goes down. So if, for example, let's say this is the population parameter, if I take, let's say population of 10,000, if I take 50 samples and look at the sample mean, it's going to be unbiased. So the mean of that will be here, but then it will have a variance like this. If instead of 50, I take 1,000, most likely I will get something like this, meaning that it's still unbiased, but with a smaller variance. So if the population from which we take the samples, if that population is normal, which is a kind of a valid assumption for a lot of situations, then you can say that the sample mean is normally distributed. It has a mean of mu, which is the population mean, and a standard deviation of sigma squared divided by n. That was a situation in which we were interested in knowing the mean of a population. What if we want to know the variance of a population? We can again do the sampling. So suppose we take a sample of size n, and we know that this quantity, this is the empirical variance, summation of all the yi's, the sample values minus the y bar, divided by n minus 1, that's an unbiased estimator. So in other words, the expected value S squared is sigma squared. Sigma squared is the population parameter. S squared is the sample statistic. So we already know that this is an unbiased estimator. However, we want to know the exact distribution. So in addition to the mean, I would like to know what the variance is going to be. So we know that the mean is going to be sigma squared. So this is the PDF of S squared. It has a mean of sigma squared, but what is the variance? The fact of the matter is finding the variance for that estimator is actually not easy. So variance of S squared is quite complicated to find. And if we don't have it, we're not going to be able to find the distribution for S squared. So what we do is usually in these statistical tests, instead of looking at S squared, we consider this new term, n minus 1, S squared divided by sigma squared. And it can be proven that if the n samples that you're taking is coming from a normal population, which has a mean of mu and variance of sigma squared, then this function will have a chi-square distribution with n minus 1 degrees of freedom. So here, instead of looking at s squared itself on a normal distribution, we look at this function, which is n minus 1 times s squared divided by sigma squared, and look up the values in chi-square tables. Another point estimator that we may be interested in is when we want to compare the variance of two populations. So imagine you have two populations. One, they have different sizes and they have different variances. You want to know how different these variances are. What you do is you take two samples, a sample of size N1 from population 1 and N2 from population 2. And ideally, you would be interested in knowing what is the difference between the unbiased estimator, which is for variance for the first sample, minus the variance of the second sample. Again, finding the difference between the two is quite complicated. So instead of looking at the difference, we actually define it as ratios. So we look at S1 squared over S2 squared. So that this would be our metric. And it can be shown, and again, we're not going to look into the detailed mathematical proof, but it can be shown that this quantity, S1 squared, which is the variance of sample taken from the first population, divided by sigma 1 squared, which is the variance of the first population, divided the whole thing by S2 squared, the variance of the second sample, and sigma 2 squared, which is the variance of the second population. This whole thing will have an F distribution with n minus 1 numerator degrees of freedom and n minus 2 denominator degrees of freedom. And usually use this test to kind of compare the variances of two populations. And the last thing we talk about is an estimator for population proportion. Suppose you have a population which is binomially distributed. You have probability of failure as Q, probability of success as P, and you want to know what that p-value is. For example, it could be what is the percentage of all the people within a population who vote for a particular candidate. You may be able to, in order to get a sense for that value, you may be able to take a sample. In that sample, see how many people vote for that candidate, and then extend it to the population. So if I take a sample of size n, and p is the proportion of success, meaning that the number of people within that sample who vote for candidate A. This would define it in a binomial distribution as a success. Proportion of success is y over n. It can be shown that the expected value of capital P is actually small letter p, which is the proportion of success for the population. And the variance of p can be found here. And again, what does this tell us? This tells us that if you want to know the percentage of success, the proportion of success in a population, take a sample, find the proportion of success in that sample, and then extend it to the population. As I mentioned before, this may not come as a surprise to you. It's something that we normally do intuitively, but now you can see that it has a mathematical proof behind it. Let's have a quick recap before we do a couple of examples. These are the column to the left are the parameters of the population, theta, which I'm interested in knowing. For example, what is the mean of a population, the standard deviation variance of a population, proportion of success of a population, the difference between mean of population one and population two. For example, what is the difference between the average heights of men in the US and in Canada? Or proportion of success in one population versus the other population. What is the difference between percentage of voters in Colorado who vote for a particular candidate versus in Utah who vote for a particular candidate? The idea is that instead of going to that entire population, we can take a sample of size n and then find that sample statistic. So instead of finding the mean of a population, I take a sample, find the mean of that sample. Instead of looking at the standard deviation of population, take a sample, find the standard deviation of that sample, find the proportion of success of that sample, find the difference between mean of sample one, sample two, proportion of success of sample one, sample two. For example, in the last example, instead of looking at all the people in Colorado who lived who voted for candidate A minus percentage of all the people in Utah who voted for candidate A, you can basically take sample and say, out of 1,000 people in Colorado, 54% voted for candidate A. Out of 1,000 people in Utah, or does not need to be the same number. Could be out of 1,500 people in Utah, 48% voted for candidate A. So the difference would be derived based on the proportions of the estimator, not the population parameter. Now, as you can see, each of these would be an unbiased estimator because expected value of y bar is mu, this one is sigma, this one is p, and so on. So all of them have the same expected value as the population parameter column to the left. The variances are also shown here. One thing for you to know is that you do notice here that a lot of variance calculations are looking into values that belong to the population. For example, I'm saying the variance for the point estimator y bar is sigma, which is the standard deviation of the population. You might be wondering, but we don't have that sigma, do we? And if you're wondering that, you're correct, we don't. Or here, for example, the standard deviation of the sample proportion of success is P times Q, probability of success, probability of failure from the population. In these situations, we actually adopt an approximate approach. So instead of calculating it as sigma over square root of n, we calculate it as S, which comes from the sample divided by square root of n. Or here, for example, we calculate it as P hat, which comes from the sample, Q hat, which comes from the sample divided by n. Or here we calculate it as S1, that comes from the sample divided by N1, and S2, again, divided by N2, and so on. It is obviously not exact. It is an approximate value, but we don't have any other options because, as I mentioned before, population parameters are generally unknown. All right, let's do a couple of activities. So consider this question. 2% of chocolate bars produced by a certain machine are deformed. What is the probability that in a shipment of 400 of those chocolate bars, 3% or more will be deformed? Let's look at this. This is a binomial process, and the sample is relatively large, 400 chocolate bars, so I can assume that it's normally distributed. Now, for the entire population, proportion of success is 2%. Success in this case is the chocolate bar is deformed. So P for the population is 0.02. Now, because sample proportion is unbiased, we can say that the sample proportion will have the same mean. So sample proportion will have the same mean, 0.02, and a standard deviation. Now, what is that standard deviation? Square root of P times Q divided by N. 2% times 98% divided by 400, that would be 0.007. So the proportion of success for the sample will be normally distributed with mean 0.02 and variance of 0.007 to the power of 2. So with that normal distribution, what is the probability that that sample statistic will have at least, 3% deformed chocolate bars, meaning that what is the probability that deformed bars is more than 3%? We standardize that and we say, what is the probability that the standard variable is greater than 0.03 minus 0.02 divided by this. So this essentially is 0.03 minus mu divided by sigma. That would be probability of standard variable z greater than 1.42, which gives me a probability of about 8%. So that means if 2% of chocolate bars are deformed, if you take a sample, there's only an 8% chance that more than 3% of them would be deformed. Let's do another example. Imagine election results show that a certain candidate has received 46% of the votes. We take a poll of 200 people at random, and we would like to know what is the probability that these 200 people would actually show a majority support for that particular candidate. So different from the population parameter. The population parameter, again, here is known, 46%. Sample distribution can be approximated as normal because the sample size is large, is 200. And again, it's normal, meaning that your sample statistic will have a mean of 4.6 and a variance, which can be calculated as square root of p times q divided by n, 46% times 54% divided by 200, which is this much. So this would be your normal distribution for the sample statistic. So the sample statistic will have, let's say this is 0.46, it will be something like this. We want to know what is the probability that I get majority out of that 200 people. Majority out of 200 people is 100 people plus half a voter, which is 100.5, corresponding to 50.25%. So what is the probability that I get 50.25%? So what is this probability? Probability that voter ratio in that sample is greater than 50% is the probability that the standard variable is greater than 50% minus the mean divided by the standard deviation, which is 11%. These two examples should hopefully allow you to kind of make a comparison between the population parameter and what you may get from a sample statistic. Now, before we go to interval estimators, let's just have a quick note here that in all these previous equations that I provided, my assumption was that it's either an infinite population or a very, very large population. If you have a small population, you have a finite population, and you're doing sampling without replacement, you need to adjust some of the equations that I mentioned before. So for example, for the estimator for the mean, y bar, if you recall, for large populations or small populations, finite populations with sampling with replacement, variance was sigma squared divided by n. But if it's a finite population without replacement, you're going to have to adjust it by this value. The same thing for the expected value of the estimator for variance and the variance of population proportion. So these terms are terms that you need to use to adjust the value of either those variances or those expected values. Okay. So far, we've been talking about point estimators. This is, you have a population, you take a sample, then you assess that sample, find its mean, variance, whatever you're interested in, and then you apply it to the entire population. Sometimes we don't necessarily want to get a single estimate. So for example, I may not be interested in knowing what is the percentage of people who vote for a particular candidate based on a sample. Instead, I might be interested in knowing what is the range of possible votes that a particular candidate might get based on the sample data. Some examples that we can have, for example, how do you call an election before all the votes are counted? Here, you don't know what the population is doing or voting. So what you can do is you can get a sample, assess that sample, and let's say that sample gives you a certain percentage of votes for that candidate. How can you extend that, generalize that to the population? What would be the ranges that you might expect from the population? Or for example, if you have a product and you want to know what the lifetime of this product is, you can take a sample, as we saw before, assess that sample, and then let's say the sample says on average this product lives for 3 years. How can you extend it to the population? What is the range of lifetime values that the population might get? Here, we're interested more in a range of values rather than one particular point. Let's uh, do this through an example of an exit poll. Suppose we have a population of 1 million voters, and we take a sample of 1,000 people, 1,000 voters, to see what proportion have voted for a particular issue on the ballot or a particular candidate. Now, obviously, if you have population of all the voters and then you take a sample, let's say 1,000 people, you might get different numbers because these are random samples. But let's say we took one sample and we got a proportion of 48%. So in that sample of 1,000 people, 48% are in favor of that particular issue on the ballot. The question for me would be, how does this value of 48% relate to the entire population? What is the probability that the actual population also votes in support of that issue on the ballot close to 48%? What is the range of voting percentages that I might be expecting from the population? And is there a relationship between that 48% and what I can expect from the population? The short answer is that yes, there is. So in this example, we know that the sample proportion is normally distributed and is unbiased. Now, for a normal distribution, which is somewhere here, the probability that you lie within 2 standard deviation of the mean is 95%. There's a 95% chance that the value of p hats that you will get, so the value of p hat might be here, can be anywhere, right? There is a 95% chance that that value is within plus minus 2 times standard deviation of the mean. And there is, of course, a 5% chance that the value that you will see will be actually somewhere outside. If there is a 95% chance that p hat is within 2 standard deviations of p, look at it another way, there is a 95% chance that p is within 2 standard deviations of p hat, meaning that there is a 95% chance that the population proportion of success p is within 2 standard deviations of the sample proportion of success p hat. So if I find 48% as the percentage of people in that sample who voted for that particular issue on the ballot, this plus 2 sigma and this minus 2 sigma could be the range of proportion of success for the population. How confident am I in this? 95% confidence. There's only a 5% chance that you will get a 48% from a sample, but then the population is outside that range. Now, let's calculate the sample. The sample standard deviation, as you saw before, is p times q divided by n. As you recall, I mentioned a couple minutes ago, for the population itself, we don't have the actual p's and q's. So what do? We'll replace it with p hat, what we get from the sample, and q hat, which is 1 minus p hat, again, what we get from the sample. So the standard deviation of the sample is 48% times 52% divided by 1,000, which is 0.015. What that means is I am 95% confident that the proportion of people in the population who vote for that candidate or that issue on the ballot would be the 48% that I got, plus minus 2 times this value that I calculated, 0.015. So with 95% confidence, the entire population will vote between the range of 45% and 51% in support of that issue on the ballot. This way, instead of me giving you a single point as an estimation, I am giving you a range of values, and associated with that range of values, there's always a confidence value. You will be within this range if you want to be 95% confident. If you want to be more confident, the range would be larger. If you're okay with being less confident, the range would be smaller. Now, here, the range, which comes as an upper bound and lower bound on the population parameter of interest, these are random quantities, and it's coming from a statistical analysis, so it does not provide any guarantees. It just tells you that the probability that the population parameter of interest is between the lower bound here and the upper bound here is this amount. Now, for reasons that will become clear to you in the future lectures, instead of saying probability is equal to some alpha or some beta, we actually say 1 minus alpha. Why we use that notation, again, we'll talk about it in the future lectures. But basically what that tells you is that theta belongs to this range with a probability of 1 minus alpha percent, or 1 minus alpha percent of the time, theta would belong to that range. This is a two-sided test because I'm interested in the lower bound and upper bound for my theta. It is also possible that I would be only interested in upper bound or lower bound. So for example, what is the probability that theta is greater than a particular number? Let's say you take a sample from a population, you look at that sample, and 52% of them have voted for candidate A. You want to know, hey, what is the probability that my theta for the population is greater than 50%? So what is the probability that I know based on the sample that my candidate will win the election? This, in fact, is the way during election season, you will see that a lot of news channels will call an election in, to the advantage of a certain candidate. This is what they do. They can say that, for example, with 99% confident that this candidate will have more than 50% of the votes, hence we call the election. Let's look at this mathematically. So if you have a large sample, all those estimators that we've talked about are approximately normal, meaning that they have a distribution like this. And what I can do is I can standardize that value. So I can say theta hat, which is my sample statistic, minus the population parameter divided by the variance of the sample statistic. If I standardize it like that, it's going to have a standard normal distribution with mean of 0 and standard deviation of 1. Now, you want to know the probability that this standard variable z lies within a range. These are provided in probability tables as numbers. For example, you have a probability, you will be between z of alpha over 2 minus z of alpha over 2 with a probability 1 minus alpha. What you do is, let's say you're interested in 95% probability. So you know that this is 0.95, which means that alpha would be 0.05. And then you go to the table and say z of 0.025, which is alpha 2, alpha divided by 2, and minus z of 0 to 5. And then you can find that value, that probability this way. So let's break it down a little. So we say probability that the standard normal variable is between these two guys is 1 minus alpha. Let's replace this with theta hat minus theta divided by sigma of theta hat. And then do a little bit of mathematical manipulation, multiply both sides by sigma of theta hat, add both sides of the inequality, add theta hat to it, and then multiply it by a negative sign. What you will get is the probability that theta, again, remember, theta is the population parameter of interest, is between sample statistic, what I get from the sample, minus this value, and plus this value is 1 minus alpha. This is your lower bound, this is your upper bound. And statistically, we say with 1 minus alpha percent confidence, my population parameter will be between theta hat plus minus z of alpha divided by 2 times sigma of theta hat. And usually, because we're doing confidence analysis, we often go with some standard values for confidence. So for example, if you're interested in being 99% sure, your z alpha divided by 2 would be 2.58, meaning that the population parameter will be between theta hat plus minus 2.58 times the variance, or rather standard deviation. You're interested in 95% confidence plus minus 2 times sigma, 90% confidence plus minus 1.64 sigma, and so on. And again, you notice the more confident you want to be in the actual value of the population parameter, the wider the range is going to be. I may be able to tell you that, for example, if this is my standard population, I can say that, hey, I am 70% confident that the value lies somewhere here. But if you ask me to be 90% confident, I will say, well, 90% confidence that it lies here. If you ask me to be 99% sure, I will say 99% sure that it's here. The more confident I want to be, the wider the range of values that I can assume. And of course, you can easily generalize this to one-sided confidence limits, probability that your population parameter of interest is greater than sample statistic minus this value, or less than sample statistic plus this value would be 1 minus alpha. We talked about, sample mean, sample proportion. We also have this interval estimate for the variance. Again, recall that for variance, we don't go with S squared because it's not easy for us to find its probability distribution. So instead, we go with n minus 1 S squared divided by sigma squared, which is chi-square distributed with n minus 1 degrees of freedom. And again, from using the tables, you can say the probability that this value is between the lower bound and upper bound is 1 minus alpha. So your interval would be, if you do some mathematical calculations, the interval for sigma squared, which is what you're interested in, the variance of your population would be this lower bound, this upper bound, with confidence of 1 minus alpha. And again, these values are obtained from probability tables. Before we close this discussion, let's have a quick activity. Imagine a sample poll of 100 voters chosen at random, have 54% in favor of a particular candidate. I want to know the limits that will give me 95% confidence for the proportion of all the voters in the population who would be in favor of that candidate. Meaning that based on that 54% out of a sample of 100 voters, can I be absolutely certain that my candidate will win based on the results of the entire election? Let's look at the analysis of this. Again, this is normally distributed. It's 100 voters, so it's a large enough sample to be normally distributed. To be 95% confident, I want to be within the plus minus 1.96 times the standard deviation. So I know that I am 95% confident that my population parameter, the total number of people in Denver who would vote for that candidate, would belong to, or not total, rather, percentage of all the people in Denver who vote for that candidate would belong to the range of what I got from my sample plus minus 1.96 times the standard deviation of the sample. I got a 54%, 1.96 times. This is square root of PQN, so PQN. And notice that again, because I don't know P and Q for the entire population, I approximate them with the values from the sample. So this is P hat times Q hat divided by 100. And I will get 54% plus minus 0.097. This is basically a number that goes from 40 something percent to 50 something, or rather 60%, 60 something percent, meaning that I know that I'm going to be between 40 something and 60 something percent. I cannot say with certainty whether my candidate will win, because if the candidate wins less than 50%, it's not going to win the election. How can I become more confident whether the candidate will win or not? So, for example, if you get to this point, and let's say you want to know if you can call the election or not, you're not going to be able to do that. Why? Because the range is very wide. In order to be able to call the election and be confident, you're going to have to increase the sample size. See what happens if I do a sample of 1,000 people instead of 100. If a sample of 1,000 people had 54%, then my population parameter would have been between 54% plus minus 1.96 times square root of this times this divided by 1,000, not 100. And it would give me 54% plus a very, very small number. That means by expanding my sample, I can actually improve my level of confidence. Hopefully, this gave you an idea of how we use information obtained from samples to generalize some conclusions about a population of interest. This is a list of references that I used for this lecture. And there are a lot of examples, additional examples provided in these that you can refer to in order to get a better sense.